Okay, so this is a review for chapter or test number 1. So number 1. So remember, the first thing you're always supposed to do for evaluating limits is to plug the numbers in to make sure you get an indeterminate result. And because we have a positive x and everything's positive here, obviously we're not going to get an indeterminate result, so we would just have 3 squared plus 6 times 3 plus 8 divided by 3 squared plus 4 times 3 plus 3. So that's 9 plus 18, which is 27. 27 plus 8 is 35. And in the denominator we have 9 plus 12, which is 21, plus 3, which is 24. And we can't simplify that down. There's no common factor. Okay, the second one. So again, we're going to first just plug in the number and see what we get. But first, let me write the problem down. So you'll see what happens is we get the square root of 16 minus 4 over 3 minus 3. Square root of 16 is 4. 4 minus 4 is 0. 3 minus 3 is 0. So it is indeterminate. So what we need to do is use rationalization because we have the square root. And what we do is we multiply by the same expression, except we change the sign of the second part. We do that in both the numerator and the denominator. So in the numerator, what we get is the inside and the outside cancel out. That's why we make this plus and that minus. When you multiply these two together, you get x plus 13, and then negative 4 times positive 4 is negative 16. And that should cancel out this term that was originally in the denominator before we multiplied anything. And what that does is it, this here is x minus 3, so that cancels out with that. And so you're left with the limit as x approaches 3 of 1 over the square root of x plus 13 plus 4. And you can see when I plug 3 in, I'll get the square root of 16, which is 4. So we get 1 over 4 plus 4, which is 1 over 8, or 1/8. So that's the answer for that one. Okay, number 3, again, we're going to evaluate this at -1 and see what happens. Now we do have we've got a negative sign here for one thing that gives us a better chance. And we've also got negative signs up here, so there's two things that make it at least more likely than the last one to give us a 0. Okay, so that's plugging in -1. So you get -1 squared, which is 1. Then you have 3 here, positive 3, because you got negative times negative. So you get 1 plus 3 is 4. 4 minus 4 is 0. And likewise in the denominator, you've got +1 minus 6 is -5, plus 5 is 0. So again, it's indeterminate and they're polynomials, so we're going to use, in this case, the canceling out technique, which means that one of the factors is associated with x equals -1 being 0. So that corresponding factor would be x plus 1, and you have that both in the numerator and the denominator. That's why you get this indeterminate result. So what do I need to multiply positive 1 by to get negative 4. Well, obviously it's negative 4, and you can see if I multiply that, I'll get that. And likewise, you know, what do I need to multiply 1 by to get positive 5? Well, the answer is positive 5. And so, if you multiply both of these out, you'll get back here. But it's always easy to factor these because this number tells us what the common factor is that's canceling out. Okay, so at that point we can cancel out the common factor. So that removes the indeterminacy. And at that point we can, now that we've removed the indeterminacy, we can just plug in negative 1. So in the numerator we get negative 5, and the denominator we get 4. So the answer's negative 4/5. Okay, number 4, the requirements for continuity, the limit. So something's continuous, basically. F of x is continuous. At x equals c if the limit exists. So you could say the limit of f of x as x approaches c exists. Okay, so the limit has to exist. It doesn't have to be, the function doesn't have to exist for the limit to exist, but for continuity we have this requirement that the limit as x approaches c of f of x is f of c. So the limit is equal to the value of the function evaluated at that value of x. And also the final thing is just that f of x exists at x equals c. So those are the 3 requirements. The function exists, the limit exists, and the limit equals the value of the function. Okay, going to the next page, we have another one of these ratios of polynomials. So first thing we need to do after I've written the equation is to plug in x equals a negative 3 and see if we get a number or whether we get indeterminacy. So we got negative 3 squared minus 5 times negative 3 minus 24 divided by negative 3 squared plus 10 times negative 3 plus 21. So let's see what we get. So you get 9 plus 15 is 24. 24 minus 24 is 0. Here we get 9 minus 30 is negative 21. Plus 21 is 0. So it is indeterminate. It also tells us that the thing can be factored. The corresponding factor to x equals negative 3 is x plus 3. So we get x plus 3, x plus 3. What number multiplied by 3 gives me negative 24? The answer is negative 8. What number multiplied by 3 times what number is 21? The answer is 7. And again, you can see if I multiply this out, I'll get x squared plus 3x minus 8x, which is negative 5x. And then 3 times negative 8 is negative 24. And you get x times x is x squared. You get 3x, 7x, which is 10x. 7 times 3 is 21. Okay, so we'll cancel those out. So what we're left with is the limit as x approaches negative 3 of the ratio of the remaining factors, but this is not indeterminate. So you just plug it in. So you get x minus negative 3. Oh, I'm sorry. Plug in the wrong place. So you get negative 3 minus 8 over negative 3 plus 7. So you get negative 11 over 4. So that's your answer. Okay, number 6. So the first thing when you have trig functions involved, which means that you have any chance of of dealing with indeterminacy, if there is indeterminacy, is to use the squeeze theorems. But the first thing you have to look at is see if you're approaching x equals 0, which you are, so that gives you an idea if that might work. In this case, there's the two theorems that says limit as x approaches 0 of the sine of x over x equals 1, and the limit as x approaches 0 of 1 minus cosine x over x equals 0. So we have to fit it into something like this, and when you have a quadratic expression, hopefully the first thing you think about is, oh, maybe should I factor that. So you can. So we know this part has to be the cosine, and this has to be the cosine, because I have cosine squared. And I have -2, so I'll put negatives right there, which fits the arrangement for the squeeze theorem, so that's good. Oh, we were supposed to plug in first, so you get 1 minus 2 times the cosine of 0 plus cosine of 0 quantity squared all over 3 times 0 squared. So here we get 1. Cosine of 0 is 1, so you get 1 plus 1 minus 2, so that is 0, and you get 0 in the denominator. So it does work out as being indeterminate. So in any case, it doesn't matter whether it's polynomials, rationals, trig functions. First, confirm that it's indeterminate. Okay, now what we can do is we can take this and break it up into 3 parts. We'll take the third by itself. We'll take one of these, 1 minus cosine of x over x's, and the second one so I've got x squared, so I've got 2 x's here, and then I've got 1 minus cosine of x. So what it says is, to finish this out, the limit of a constant is just the constant. This is 0, this is 0, so the answer is 0. Okay, number 7. This is a one-sided limit. So the only thing that you do differently is, if you get what is the difference here? It's very similar, except unless you divide by something divided by 0, and then you have to figure out whether this goes to plus or minus infinity. So you can see if I plug in -6, I'll get 6 minus -6 divided by -6 squared minus 6 minus 30, and what that gives you is 12 over 0. So it's not indeterminate, it's undefined. So as a consequence, now we can factor the denominator if it's possible. So we'll get 6 minus x over x minus 6 and x plus 5. So you can see this factor is the 1. Is that true? X plus 6, x minus 5. I knew I had done something wrong because I had to get 0 in the denominator somehow. Okay, so if you plug -6 in, you'll get 0 here. So what you need to do is look at the sign of each one of these. So you'll have 6 minus a -6. So the numerator is going to be positive because you got 6 plus 6. That's how we got the 12 initially. This one you're going to put in -6 and you're going to subtract 5. So -6 minus 5 is definitely negative. And then you've got this one, and so because we're approaching -6 from the positive side, that would be like -5.9. This term's going to be positive because you have negative 5.9 plus 6, which would be positive 0.1. So once you've got the signs of each one of these parts figured out, you can just count up how many negative signs you have, which is 1. So that's odd. Therefore, the answer is undefined, but it also is negative infinity. So it's an asymptote that goes down. Okay, next one, find the vertical asymptotes. So that's pretty easy. All you have to do is really just factor the denominator. I guess you have to factor the numerator to make sure that there's not a common factor. That would be indeterminacy and not vertical asymptote. So the numerator and the denominator. So two numbers multiplied together give you negative 12. Added together give you negative 1. So that would be it. Two numbers multiplied together give you negative 14, but added together give you negative 5. So you get that. And you can see there are no common factors, so the vertical asymptotes are vertical lines. So you set both parts equal to 0 in the denominator. So you get a line x equals 7. That's the vertical asymptote. Here you get x plus 2 equals 0. So you get x equals negative 2, which is the other vertical asymptote. Okay, number 9, another one-sided limit. The limit is x approaches 4 from the negative side of 2x plus 5 divided by x minus 9 x minus 4 squared. So you can see that if I plug 4 into the numerator, I'll get some positive number. I'll get 9, I guess, or 14. 8 plus 5 is 13, positive. This will be, well, what we're doing right now is just to see whether it's undefined or not. You can see if I plug something in here, I'll get 0. 4 minus 4 is 0. So this means it's undefined. Okay, so that means I need to figure out which way it's going. And again, what I'm going to do is I'm going to first, for all the cases except here, I'm just going to plug in 4. So yeah, let's just do that. So if I plug in positive 4 here, I'll get a positive because I have 8 plus 13, which is positive. Now here I can plug in 4. 4 minus 9 is negative 5, so that's negative. And you can really say that's positive because anything squared is going to be positive. So again, we have an odd number of negatives, so the answer is negative infinity. Okay, number 10 is another rationalization, possibly. Depends on if we get an indeterminate result. And you can see, just looking at it, you've got 5 plus 59 is 64. Square root of 64 is 8. 8 minus 8 is 0. And 5 minus 5 is 0. So it is indeterminate, so we have to use rationalization again. Rationalization. So we take the term that involves the square root. We multiply it by the same expression, except we change the sign to the second part. We have that original denominator and we multiply by this same thing that we're using to get rid of the square root in the numerator. So what happens is these multiplied together give you x plus 59, and then you got minus 64. Negative 8 times positive 8, the inner and outer cancel out. You get x minus 5 times the square root of x plus 59 plus 8. But that is the same as that. So we get rid of the indeterminacy. You get 1 over the square root of x plus 59 plus 8, which is 1 over 16. Because this will be square root of 64, which is 8. 8 plus 8 is 16. Number 11. So this is another one of those trig ones, but you should have seen right away that because it's not going to 0, you just plug the numbers in. So what you get is you get the sine of 3 times pi over 6 quantity squared. So I'm rewriting sine squared as the sine quantity squared. And then I have 3 times x, which is pi over 6, and that's squared. Now, here we have 3 pi over 6, which is pi over 2. The sine of pi over 2 is 1. So we'll get 1 squared. In the denominator, we'll have 3 pi squared divided by 6 squared. And you can see we can take the reciprocal of the denominator, and then you can simplify. So you get 12 over pi squared is your answer. The key thing was to recognize that that's not going to 0, so you can't use any squeeze theorem stuff. And then your final problem is looking at the two types of discontinuities, which are removable and non-removable. So it means we're going to factor the numerator and the denominator first. So we get, well, two numbers multiplied together give us 14, and add together to become 9. Get that. And then what two numbers multiplied together give me 6, negative 6, added together give me negative 1. So that's that. So you can see there's a non-removable at x equals 3. That makes that go to 0, and I can't remove it. So this is a vertical asymptote. This is a removable discontinuity. So we have a removable at x equals negative 2. So now the question is, how do you remove the discontinuity? Well, you evaluate the function at negative 2 after you've simplified it. So what we're going to do is we're going to evaluate it at negative 2, but we're going to cancel those out. Otherwise you'll get an indeterminate result. So what this is basically evaluating the limit of this original function as x goes to negative 2. So we can plug those in there. You get negative 2 plus 7 over negative 2 minus 3. That's 5 divided by negative 5, negative 1. So that's the same as the limit of f of x as x approaches negative 2. So using the canceling out thing. So the way you would do it, the way you would redefine the function, is you would break it up into 3 parts. So the function would be the original function. Well, you actually have to break it up into 5 parts because you've got a discontinuity here at non-removable at x equals 3. So what we'll do is we'll take the original function. That's good from negative infinity to negative 2. When x equals negative 2, the function equals negative 1. Then again, the function is normal between between -2 and 3, where the non-removable discontinuity is. And the function does not exist at -3, so we won't include that in our domain. So this is from 3 to positive infinity. So this is where the removable discontinuity is. We removed it by defining the function at that point to be equal to the limit of this original function. At x equals 3, it's a non-removable discontinuity, so we just have to reflect the fact that the domain is such that the function does not exist at that point. So that's it.